In this part, we're going to be talking about ways of expressing concentrations of solutions. And this goes back to your first chemistry course where you should have learned about molarity. And so, one of the first things we're going to look at is molarity. Now, molarity is expressed in moles of solute per liter of solution. What's important for us in this chapter is that we have to understand what the solute is and the solution are. So solute is the part that's being dissolved, and the solution is the entire thing combined together. Now, one thing that we didn't talk about in chemistry one with molarity is the fact that molarity is dependent on the temperature, and so that should make sense because as you change the temperature, you're going to change the volume of a substance, or in this case, the volume of the solution. And as you change the temperature, you're going to ultimately affect the molarity of that solution. So at a colder temperature, the volume is going to be smaller, so the molarity will be higher. At a higher temperature, the volume is going to be larger, so molarity would be a lower concentration. It's not going to be lowered by a substantial amount, but it definitely would be lower than your normal, which would be at 25 degrees Celsius. So you have to take that in consideration. Now, again, molarity is moles of solute per liter solution. In chemistry one, you probably learned it was just moles per liter. In this part, we have to understand what the solute is and what the solution are, because that is going to play a role in the near future as we start getting into other concentrations. So now mass percent is the generic formula is mass percent of A, so A is anything, is where you take the mass of A divided by the total mass times 100. And so if we had, let's say, 10 grams of sodium chloride and 100 grams of solution, what would be the percent mass of NaCl? Well, the percent mass of NaCl would be equal to 10 grams divided by the 100 grams times 100, which would be 10% NaCl. So that would be the mass percent of NaCl in solution. So it is that easy to figure out what mass percent is. So now, adding on to that, we have a problem here. This problem states aqueous ammonia is commercially available in a solution that is 28.0% NH3 by mass. What is the molarity of NH3 in this solution? So there's a few things that are given to you. First thing is to tell you the percent mass of NH3. The second thing is they give you the density of the solution. And the question is, what is molarity of NH3? And so to answer this question, we have to start off with what we're given to work towards the answer. So we know that molarity, as we just talked about, molarity is the moles of NH3 divided by liter of solution. So those are the units that we want to get to in order to answer this problem. So what are we given? So first thing, we're given our percent mass. That means that we have 28 grams of NH3 per 100 grams of solution. That's the first thing. So we have to take the percent and write it in this form that you see here. The second part is the density. So now we're going to introduce the density here. So the density is 1.165 grams of solution divided by milliliter of solution. So this density is of the solution. That's why this is important. Now what we're going to see here is that units are going to start to cancel. Now the grams of solution will cancel the gram solution here. Now we see that we have grams of NH3, we have milliliters of solution. Now our goal is to get moles of NH3 over liters of solution. So first thing we're going to do is we're going to convert milliliters into liters. So there are 1,000 milliliters per liter. And so you see that the milliliters are going to cancel out here. And that gets us into liters. And then we need to go convert grams into moles. That was a roadmap that you should have learned. So convert grams to moles, we're going to divide by the molar mass of NH3. Use your periodic table, figure out the molar mass of NH3. Nitrogen's 14, hydrogen's 1, there's 3 of those. So 14 plus 3 gives me 17 grams per mole. So for every mole of NH3, there are 17 grams. So now the next thing we're going to do is we're going to take 28 divided by 100 times 1.165 times 1,000 divided by 17. Now, if you do this correctly, what are you going to get? And I will do that with you right now. So you're going to get roughly 19.2 molar NH3. So that is the molarity of that solution. So what does that mean? That means that for every liter of solution you have, you're going to have 19.2 moles of NH3. And this is a good example of a commercially stock available solution. So this is what the highest concentration for that particular NH. And this would be very high concentrations. This would knock you off your feet if you were actually to inhale it. When we talk about ammonia smell, we have 5% by mass at the store. So you open a bottle of ammonia at the store. It's not. Some people like it. Some people don't like it. It's still a strong smell. This one is quite a few times higher, and this is about 5 times greater in concentration. So definitely something you don't want to intake to your lungs. That would not feel good. So another unit of concentration is parts per million and parts per billion. These are based off of the mass percent. You can see how they're very similar, but the difference here is when you're dealing with parts per million, you take the mass of A divided by total mass solution times 10 to the 6th. If you were to deal with parts per billion, you'd multiply by 10 to the 9th, because 10 to the 9th is a billion and 10 to the 6th is a million. So an example would be a 2.5 gram sample of groundwater was found to contain 5.4 micrograms of zinc 2+ ions. What is the concentration in parts per million? So in this problem, you have 2.5 gram sample, and then in that sample you had 5.4 micrograms. So what we need to do is convert this into grams. We need to get the units where they're similar to each other. So there are 10 to the 6 micrograms per gram. So what we need to do is basically divide that out, and what we'll end up with is 5.4 times 10 to the negative 6 grams. So that's how many grams it would be. So we would take this number here and we would divide it by 2.5 grams, and then we would take that number and we would multiply it by 10 to the 6th, because we want it to be in parts per million. So we would end up with 2.16 parts per million. So that would be the concentration here. Now, what does that mean? That means that if you were to count 1 million particles that goes by, 2.16 of those would be zinc ions. No, so that represents a very small amount in retrospect to a million. And so I don't think I'd want to lose track of counting here. That'd be kind of tough. Let's recount that again now. No way, Jose. 2.16 parts per million. Now, if we were to convert that into parts per billion, well, the difference is 10 to the 9th. That's the difference of 1,000. So once we know the parts per million, just take that number, multiply by 1,000, and then you have your parts per billion. And so in this example here, that means that 2,160 parts per billion. So for every billion things that goes by, 2,160 of those would be zinc ions. So that's another unit. We use parts per million, parts per billion when you're working with very small units. So you don't need it if you're working with something that's much higher in concentration. Molarity would be a good factor there. So we had a previous video. I'd take a second and answer these questions. All right, so name 3 factors that affect solubility and give one example of each. All right, you can work on that. Number 2 says, what does parts per million mean? If I measure 10 grams of water from Tuckasegee River and found it that contained 5 nanograms of iron, what would the concentration be in parts per million? What I want you guys to do with this is I want you to write in the comments what your answers are for the first and the second answer, or second question. So moving on with concentration, we have mole fraction. Mole fraction is the moles of A divided by the total moles. Now, if you know the mass, you're going to need to make sure you convert your grams into moles first, using the roadmap that we just talked about in the previous slide. So mole fraction, all right, if I were to have 1 gram of ethanol, so let's say I have 1 gram of ethanol, which is CH3, CH2, OH, and 100 grams of water, what would the mole fraction be? So what we need to do first is you need to convert your moles of ethanol, or you convert grams of ethanol into moles of ethanol, then convert your grams of water into moles of water. All right. So the moles of ethanol, so the molar mass of ethanol is 46.07 grams per mole. We're going to take the 1 gram and divide it by that 46.07. And so the moles of ethanol are 2.17 times 10 to the negative 2. And the abbreviation for that is ETOH. And now we're going to divide it by the moles of water. Now the moles of water, you're going to take 100 grams of the water, and you're going to divide that by 18 grams per mole. That way it gets you into the right unit. And so if you do this correctly, what you end up with is 0.990% ethanol. So again, well, not percent. I'm sorry. This is not percent. It's just a mole fraction. In fact, this is not even the right number. Looking at the wrong one. So 0.00389 would be the answer for that mole fraction. So a very small fraction there. Again, there's very few moles of ethanol compared to the number of moles of water. Now you could figure out the mole fraction of water with respect to ethanol, where you just flip the things around. You'd have the moles of water on the top divided by the total moles of the solution. And so this needs to add in the 2.17 times 10 to the negative 2 moles of ethanol. So you do need the total moles in the solution. All right, now the next thing here is that when you're working with mole fraction, you don't always have to use the solute. All right, sometimes you're going to be using the solvent. And so the reason for that being is we'll be talking about collective properties in a future video. And so you have to and when you're dealing with Raoult's law, you have to look at the solvent as compared to the solute. All right, our next unit is going to be molality, and molality is expressed as moles of solute per kilogram of solvent. A little different from molarity, which was moles of solute per liter of solution. Now, what's also unique about this is that, remember, molarity is temperature dependent. The units for molality have no dependency on the temperature. So, unlike molarity, the molality is not going to change in its value. So now we have to, in order to figure out the molality, you have to first know the moles of solute. In this case, we can use the ethanol. So you have 1 gram of ethanol per 100 grams of water. So we calculated the moles of ethanol to be 2.17 times 10 to the negative 2 moles. Now, we need to know the mass of water in kilograms. So water is your solvent. So 100 grams is going to be converted into 0.100 kilograms of water. So we take 2.17 times 10 to the negative 2 and we divide it by 0.1 grams. And so what you end up with is 0.217 molality. And so, yeah, the symbol for molality is actually an italicized M, but I don't typically like to use that because sometimes you can confuse it with meters, and so I like to write it as molal. It means the same thing. It doesn't really change anything. It's just a difference of how we express the unit. So, but molality is again is moles of solute per liters or per kilogram of solvent. Molarity is moles of solute per liter of solution. It's really easy to say that because it's just been instilled in us. So, but molality is going to be used when we start discussing colligative properties in the near future. So it's one unit that you want to try to get comfortable with and expressing. So now I want to do an example here, and so this is a little flow chart we can use for this example, but it's going to be similar to one that we've already looked at before. So let's say we have 20% by mass of HCl, and let's say the density of this solution was 1.25 grams per milliliter. So this is the density of the solution. That was the percent mass of HCl in that solution. The question is what is the molarity of HCl in this stock solution? So again, we have to look at the two things that are given to us. We have to understand that the percent mass is 20% HCl. And so what does that mean? That means that you have 20 grams of HCl for every 100 grams of solution. And then we're going to multiply that by the density, which was 1.125 grams per milliliter of solution. Now, you notice the grams are going to go away. And so now what we've got to do is convert our milliliters into liters. So there was 1,000 milliliters per liter. And then the molar mass of HCl is 36 grams per mole. So for every mole of HCl, we have 36 grams. So the grams there is going to go away. The milliliters are going to cancel out here. So now all we have to do is go through the calculation to 20 divided by 100 times 1.125 times 1,000 divided by 36, and what you should end up with is 6.3 molar HCl. So that's another example of how we would go through using the percent mass, using the density, and calculating the overall molarity of a solution. Now, if I were to ask how would you calculate the moles, the molality of HCl, well then you have to have a little bit more information given to you. And so again, remember, molality is moles of solute per kilograms of solvent. So I hope that this helps with your understanding of the different concentrations and how they're expressed. So if you have any questions, make sure you comment or email. Thanks.